This lesson is on navigation plotting. So far in your studies, you have become aware of two methods of navigation. One is solo pilot VFR navigation, based on the 1 in 60 rule. The other is the use of automatic computing systems, such as INS, IRS, FMS, GPS, and RNAV. However, there is a whole group of aircraft which are more sophisticated than light training aircraft, but less sophisticated than the full jet airliner glass cockpit standard. These aircraft are routinely fitted with VOR, DME, ADF, and gyromagnetic compasses. For this sort of intermediate complexity aircraft, it becomes necessary to plot on a radio navigation chart, or a specialist plotting chart, usually a Mercator's chart or a Lambert's conical orthomorphic chart. The EASA ATPL requirement is for the use of the Lambert's conical orthomorphic, and occasionally the polar stereographic. The chart used for most of the question settings is the Jeppesen ELO1. Any charts used in the exam will be supplied as an annex to the question paper. If plotting is required on any other charts, appropriate annexes will be attached. These are usually skeleton charts or small-scale Jeppesen charts. You will need the following equipment: a navigational straight edge, a square plotting protractor, dividers for measuring, a pair of compasses for drawing DME range arcs, 2 H and HB pencils for plotting, and a soft eraser. The task required is usually not difficult. It may involve, for instance, plotting a VOR DME crosscut, or possibly 2 VOR radials. Sometimes the question is asked in reverse. You are given a position in latitude and longitude and asked to select the correct 2 radials. You will need to know your basic cartographic symbols. You will become familiar with these and other types of question as you try the practice questions associated with this lesson. However, although it is usually easy to understand what is wanted, sometimes the difference between a right and wrong answer is only 2 degrees. It is essential to plot accurately. Bearings can be split into subcategories: relative, or with respect to north, true or magnetic, measured at the aircraft, or measured at a ground station. Each of these considerations affects how we plot them. We'll start by considering relative bearings. There are 2 instruments that may be used for displaying bearing in the aircraft. These are the well-known radial magnetic indicator, or RMI, and the older relative bearing indicator, or RBI. The RMI has a rotating compass backplate, which is driven from the gyromagnetic compass or directional gyro indicator. If correctly synchronized, it continuously shows the aircraft's magnetic heading. In front of this rotating compass indication, there are VOR or ADF needles, or both, depending on the aircraft's navigation fit. We will assume 1 VOR pointer and 1 ADF pointer. The magnetic direction to the navigation aid is read directly off the pointed end of the needle against the compass backplate. Therefore, in this example, the magnetic direction to the VOR is 270, and the magnetic direction to the NDB is 000. Alternatively, you can use the tail end of the needle to obtain the magnetic direction from the navigation aid. In this case, the magnetic direction from the VOR is 090, and from the NDB, it is 180. By contrast, the relative bearing indicator, or RBI, has a fixed backplate, which always shows 0 at the 12 o'clock position. It can display only ADF bearings. The 0 represents the longitudinal axis or heading of the aircraft. The bearing is given as an angle measured from 0 to 359 degrees clockwise. This is called the relative bearing. In this example, the relative bearing is 030. We'll assume that the aircraft is on a heading of 045 degrees magnetic. The relative bearing of the NDB is 030. You can see that this gives us a magnetic bearing to the NDB of 075. This gives us the method of converting a relative bearing into a magnetic bearing. You add the relative bearing to the magnetic heading. If the answer comes to more than 360 degrees, you subtract 360. In this example, we have a magnetic heading of 315 degrees. The relative bearing is 130 degrees. Adding them together gives 445 degrees. We subtract 360 to give a magnetic bearing of 085 degrees. The RBI and the pointed end of the RMI needles give QDM. This is the magnetic track to the VOR or NDB. This is useful for homing to a facility, but not for plotting. We have to measure bearings from the navigation aid, not the aircraft, because it is the VOR or NDB which is printed on the chart, not the aircraft position. We therefore need the bearing from the VOR or NDB. If the information is presented as a QDM, we must convert it to a QDR. As these examples show, this is simply achieved by adding or subtracting 180 degrees. The only raw information which comes in the form of true bearing is the QTE, which is a VDF response to a pilot's transmission. As this is a true bearing from the ground station, it can be plotted directly. All others are in the form of a QDM or a QDR. As we have already said, your first task is to convert any QDM into a QDR. We now have a magnetic bearing from the navigation aid. There are 4 possible ways to plot it. You could align the protractor with a magnetic north arrow, if there is one. The problem is that these tend to be very short, usually just over 1 centimetre, and it is difficult to align the protractor accurately. Remember, we said that accuracy was important. A better method is to find the variation from the isogonals. Then use your protractor to plot the variation at the VOR using the nearest meridian as true north. You now have a magnetic north arrow, but a much more accurate one. You can plot the magnetic radial directly without needing to apply variation arithmetically. In this example, a magnetic radial of 108 degrees is shown. However, if the VOR is on an airway, or better still, is positioned on several intersecting airways, then the airway centre lines will be defined by printed radials on the chart. Take, for instance, Shannon. There are radials of 052 magnetic, 071 magnetic, 080 magnetic, 115 magnetic, and 173 magnetic. Put the centre of your protractor over the VOR symbol and then turn it until the 052 on its scale goes through the 052 radial. The 071 goes through the 071 radial, and so on. You have now aligned the protractor with the same magnetic north that Jeppesen have used, and you can now plot a magnetic radial directly. Alternatively, you can convert the magnetic radial to a true bearing by applying variation arithmetically, and then plot by lining up the protractor grid lines with the nearest meridian. In this example, with a variation of 8 degrees west, a magnetic bearing of 108 becomes a true bearing of 100.